by Archisman. Thank you.
Is it on now? I think it's on now. Bring it a bit closer. I'm sure it's on now. I can hear a echo. So, I'd like to thank the organizers for putting together this wonderful program. It's a pleasure to be here in the center. This is my first time here, and hopefully not the last time, hopefully only the first time. It's, I will mainly be talking about standard siren cosmology. I was initially planning to talk about a bit of fundamental physics with gravitational waves, but I decided to do justice to one topic, and I'm sure that Luis is going to talk a lot about fundamental physics with gravitational waves later in this colloquium. So I'm going to give a brief review of the experiment and observations. I'm going to spend most of my time on standard siren cosmology and then go over to some future prospects. With apologies to those of you who have listened to my talk last week, I'll begin with an overview of the gravitational wave experiments, the current generation of the current experiments LIGO, Virgo, and Kagra. So most of my talk is going to be on data analysis and observations, but it's I think it's important to appreciate that we are making a really precision measurement with these interferometers, these interferometric detectors, which are L-shaped detectors with laser beams shooting across two perpendicular arms, coming back and interfering. And with these interferometers, we are able to measure relative deformations or strains or of the order of 10 to the minus 21. These detectors are typically 4 kilometer long, so that means we are able to measure distances of the order of 10 to the minus 18, so that's a kilometer times 10 to the minus 21, 10 to the minus 18 meters. That's 1,000 times smaller than the nucleus of an atom. On the right, we see the typical sensitivity curve of the detector, which is actually tells us about how high the detector noise is. So, in fact, this bucket in between the high noise areas is our sensitivity region, and we see that we are most sensitive for these ground-based second generation detectors in the region of around 100, 200 hertz, so about 20 to 1,000, 2,000 hertz. We currently have a network of 5 detectors which are operational or which are going to be operational as soon as our next observing run starts. And of the 5 detectors, 4 of them are really science detectors, and there's a GEO 600 detector in Germany, which is mainly used for testing various components that eventually get installed in the other detectors. And a 5th science detector is planned to come up in India. The data from all of these detectors is analyzed by a global collaboration with from around 30 countries, from 30 countries all over the world, including Brazil here. The gravitational wave sources which we expect in this region, in the region of 100 hertz-ish, they fall into 4 categories. So these also define 4 of the data analysis techniques that go into our gravitational wave data analysis. They are compact binary coalescences, so mergers of binaries of black holes or neutron stars, which we have already detected. However, there are other sources which we also expect in this band, which we have not detected yet. These are bursts. So these would be explosions which are not really modeled, for example, explosions from core collapse supernovae. Continuous gravitational waves, so gravitational waves from, for example, a neutron star which is not perfectly symmetrical spinning. Because it's not perfectly symmetrical, there's an asymmetry, because of this asymmetry, there's a change in the quadrupole moment, which is the sense of gravitational radiation. So we should see very continuous sinusoidal gravitational wave of constant frequency from these sources. And moreover, we also expect to see a stochastic gravitational background. A part of the stochastic gravitational background is expected to be cosmological, coming from the very early universe, but in the LIGO-Virgo band, it's expected to be drowned in an astrophysical background coming from the superposition of all other gravitational wave sources. So these compact binary mergers, they go through, they are the last stages of the merger of a binary that has probably been in its orbit for millions of years. And as it has been going around, it's been radiating gravitational radiation. And due to this energy loss, it has been falling in. And as it has been falling in, it is moving faster and faster. So it goes through the final cycles of in spiral and then plunges into a merger. And finally, one black hole is formed, which slowly settles into its final state, giving out the last bits of gravitational radiation and settling down into its final state. The gravitational signal from this merger is a characteristic chirp signal, so-called because it's of the fact that its amplitude as well as its frequency increases with time. And on the plot in the bottom over here, we see how this particular signal from the first detection swept chirp in this time frequency plot. Both the frequency increased with time, consistent with the fact that we are in the 100 hertz region and with a period of about 0.3 seconds. Now, for these signals, the signal can be modeled very accurately by a combination of analytical numerical methods. In fact, two of the organizers who are here are some of the authorities on modeling these signals in different ways. Because this signal can be so accurately modeled, it is possible to search for these signals even when the signal is as small or smaller than the noise around it by a method called matched filtering. So I think the animation will work. So here we see a train of data with some signal within it. You do not really see the data within the signal, but as you run a template through the data where the signal is located, we see a peak in the cross-correlation function telling us that there is some something interesting, some data within the signal at that point. Of course, we do not only want to know where there's a signal where there isn't. We want to know what kind of source the signal came from. And the signal carries information about the parameters of the system. What kind of parameters of the system? The intrinsic parameters of the system that really belong to the system, like the masses of the components which are about to merge, the angular momentum of these components. These are for black holes. And if you're going to neutron stars, also tidal parameters, how these neutron stars, how easily these neutron stars can be deformed. And if we want to look beyond standard physics, then one can also put in additional parameters beyond generativity. And there are also extrinsic parameters, which are not parameters of the system itself, but which are more about where we are located with respect to the system. So the distance to the source, the sky location, the inclination angle, how the source is oriented with respect to us, and the polarization, the relative polarization between two directions given a coordinate system, and such. So with these two aspects, a rapid search and a rapid as well as a low latency parameter estimation. We have a complete workflow for data analysis of compact binary coalescences. So as the signal is coming in, we search through the signal, try to find interesting triggers. We try to rank the triggers. And of course, some of the triggers are false. We try to characterize triggers by a false alarm rate. And on the interesting triggers, we then carry out parameter estimation at low latency, which is given out to astronomers for electromagnetic follow-up in case there's a possibility of a coincident electromagnetic radiation. And on a higher latency over a longer time, we perform thorough Bayesian parameter inference, and out of this we extract essentially the results that come results on fundamental physics, astrophysics, and cosmology. Between 2015 and 2020, we have had 3 observing runs with increasing sensitivities. Our sensitivities are often characterized by the binary neutron star range, the distance to which we can see binary neutron stars given a sensitivity curve. And as you can see, the binary neutron star range has been increasing over the 3 observing runs. And the detection rate has also been increasing over the 3 observing runs. And we have ended up with about 90 detections at the end of the 3rd observing run. The discovery of gravitational waves in GW 150914, it was of course the first direct detection of gravitational waves. It was the first direct observation of a black hole. It was the discovery of a class of heavy black holes of mass greater than 30 solar masses. These black holes were not expected in conventional astrophysics. It was the first observation of a black hole in a binary, and it was the first observation of a black hole forming. The 2 black holes merged and formed a remnant black hole, and we could really see how we can really see how a black hole really oscillates as it is formed. And this tells us, as we heard yesterday, about fundamental physics and no-hair theorem. We already had 2 more signals in the first observing run, and one thing I'd like to point out here is that signals which are of lower mass, lighter signals, they merge at higher frequencies, so they tend to spend more time in the observable band. One can do a calculation to see this, but there's also a simple way to see this. This comes from a very simple scaling, that in general relativity there's no scale other than the gravitational constant. So one can work with units where the gravitational constant is set to unity, and in these geometrized units, mass and time have the opposite. Mass and time have the same scaling dimension. So mass and frequency have the opposite scaling dimension, and frequency just goes as 1 over mass. So heavier black holes, they coalesce at lower frequency. Lighter black holes, they coalesce at much higher frequencies. And we had many more similar detections in the second observing run. Of course, the highlight of the second observing run was the binary neutron star merger, GW 170817. And here we see the gravitational wave chirp from the binary neutron star merger. It's a much longer signal. It goes on for about about a minute or longer, and already telling us that it's potentially a binary neutron star. But because it's not just gravity, because there's also matter colliding, one can expect other kinds of radiation, for example, an electromagnetic radiation, or even neutrinos following the merger. In fact, we were not so lucky to observe neutrinos from this, but after about 2 seconds after the gravitational wave signal, there was a gamma ray burst, and about 10 hours later, this patch of the sky was being followed up, and an optical counterpart was observed. The optical counterpart was quickly identified to a host galaxy, and this optical counterpart slowly or faded away from optical to near to far infrared, eventually emitting radio afterglows much later. So essentially, this counterpart was observed in practically all bands of electromagnetic astronomy. This gave birth to multi-messenger science with gravitational electromagnetic waves and confirmed binary neutron stars as progenitors of short gamma ray bursts. It demonstrated that they were prolific sites of heavy element formation. In the plot for the kilonova, which you saw earlier, one can see these spectral lines, and from these spectral lines, one can infer that, what kind of heavy elements exist in these in the region after the merger. And it constrained the speed of gravity with respect to the speed of light. The gravitational electromagnetic signal, they arrived essentially at the same time after traveling for millions of years, which demonstrated that gravity and light propagate with the same speed. It provided an access to the elusive neutron star equation of state, which is otherwise very difficult to measure either on laboratory experiments or also difficult to calculate by lattice QCD techniques. And finally, it provided a novel measurement of the Hubble constant in cosmology, which is going to be the topic of much of today's talk. Some of the more recent highlights from the third observing run were, these are some of the detections from the first half of the third observing run. And among the exceptional ones are GW 190425, which is a potential BNS, but we do not really know whether it is really a BNS because we could neither measure tidal parameters nor see a counterpart. However, its masses are consistent with it being a binary neutron star merger. However, it is a bit heavy compared to all other binary neutron star mergers which have so far been observed in electromagnetic astronomy. Then there was GW 190814, a highly asymmetric system for which the lighter object was in the putative mass gap between neutron stars and black holes. This even further had a mass ratio of greater than 9. So the heavier object was 9 times heavier than the lighter object. And with these high mass ratios, as we also heard yesterday, we can infer higher modes in the gravitational wave signal. And for this particular system, we had a clear identification of the 3-3 mode in the gravitational wave signal. And perhaps the most interesting one was GW 190521 with black holes, with the progenitor black holes of masses around 85 and 65 solar masses, and the remnant in around 150 solar masses, clearly in the intermediate mass black hole region. In O3b, we observed at least 3 mergers of black holes and neutron stars. So O3b has also given us something new. And here in the colored contour, we see the 3 objects which are clear, in which clearly one of them is a black hole masses of around 20-30 solar masses, and the other one a neutron star much lighter. There are a few others where we do not know whether one of the objects is in the mass gap or is really a neutron star. So we have of the order of 90 events, 90 detections now. We can start doing a lot of science where the number of detections matter. And these include some of the tests, some of the tests of generativity which we are performing, where we can combine or stack information up from multiple observations. Here we see a plot that constrains from propagation effects various parameters that are inconsistent with Lorentz violation, and essentially one parameter which is consistent with Lorentz violation but gives a mass to the graviton. So these terms can be constrained, and we have a constraint on the mass of the graviton, which you see over here. Then with these large number of observations, we are able to infer the population, the astrophysical population of these binaries. And the plot over here shows the mass distribution of the primary, of the heavier of the two objects which are merging. And it, although it is not very clear at this stage, we kind of see a small feature, a small bump in the mass distribution at a certain mass beyond the power law decay. And we have cosmology from gravitational wave observation. We have cosmology from these observations where we also combine information from various events. And here is the latest measurement of the Hubble constant, which is, as I said earlier, going to be the topic of the bulk of my talk. With this introduction, I'm going to go over to standard siren cosmology. And I'll explain what standard sirens are, and then how we use, I'll talk about bright and dark standard sirens. We already heard about some of this on Monday. And then I'm going to talk about the current results. So what are gravitational wave standard sirens? Probably the first thing that you notice when you see this signal is that the signal is characterized not only by an amplitude, but by a phase. So our detectors are sensitive not only to the total intensity or the amplitude, but also to the phase evolution. And essentially this phase evolution carries information about the system, in particular about how heavy the system is. As I said earlier, a heavier system chirps much faster than a lighter system. Of course, that's the leading order effect. There are higher order effects, but the phase evolution gives us a very accurate estimation of the intrinsic mass of the components. Now we can use this mass which we obtain from the phase evolution and plug it back into the amplitude, and we know that the amplitude has to fall off as 1 over distance. So together with the phase and the amplitude information, we can estimate the distance to the object directly. Directly meaning with only these gravitational wave signals and without any distance ladder, which is necessary in measuring distance in most of the rest of astronomy. For those of you who are unfamiliar with the distance ladder, this is how it works. We use nearby objects to calibrate objects that are further away, and we then there's an overlap region. We take these objects which are further away to calibrate objects that are that are even further away. So we start off with very local ways such as ranging and parallax, go over to certain other indicators, and then finally to Cepheids and supernova, and which are at each point we try to come up with some sources which are standard or standardizable. So these are standard candles in electromagnetic astronomy. In analogy to standard candles, gravitational waves are standard sirens, but for standard sirens, this kind of a distance ladder is not required. We directly measure the distance with the standard sirens. Now you would also know that with measurement of luminosity distance and redshift, we can come up with a redshift distance relation on the observational side. And on the theoretical side, this redshift distance relation depends on the parameters of cosmology. What parameters in cosmology? The expansion and the acceleration parameters, so essentially the Hubble constant in the local universe, and parameters like the matter density, the dark energy density, and the dark energy equation of state. So with standard candles, one can measure the Hubble constant directly in the local universe. There's also a way of measuring the Hubble constant, not directly but indirectly, from the very early universe using CMB data, for example, from Planck. So that measures the Hubble constant in the very early universe, and using a cosmological model, such as the lambda CDM model, one can extrapolate that and obtain the value of the Hubble constant in the present epoch. One would imagine that these two values of the Hubble constant would agree. However, as experiments have become more and more precise over the past decade, the Hubble constant from nearby observations and the Hubble constant from cosmological observations have started to disagree. And this disagreement has increased to something around 5 sigma in the recent years. So in some sense, cosmology is calling out for new probes, and gravitation waves is a new probe that can provide insight into this Hubble tension. For a Hubble constant measurement, or measurement of cosmological parameters in general, along with the distance, we also need a redshift. The question is, where can the redshift come from? We know in electromagnetic astronomy, there are spectral lines, and by redshift, we mean if an object is moving away from us, for example, due to cosmological expansion, the spectral lines are shifted to a lower frequency. We can see how much the spectral lines are shifted, and we can directly read off the redshift. The question is, are there similar spectral lines for gravitational waves? The answer is, for binary black hole mergers, there are no spectral lines, essentially because there is a redshift. However, the redshift is totally degenerate with the mass of the system. This is same as the scaling that I talked about earlier. There's only gravitational constant, no other scale in the system. So looking at only the frequency, we cannot tell whether an object is heavier or an object is slightly lighter but placed further away so that it's experiencing a higher redshift. Both these effects, and heavier object would merge at lower frequencies. An object that is farther away but lighter but redshift would also be redshifted to lower frequencies. These effects are totally degenerate for black holes. Now, this degeneracy is broken for neutron stars. This is not exactly the case for neutron stars, because neutron stars have their internal physics. So one can think of tidal effects in neutron stars associated with a certain scale. One can look for resonances within neutron stars. So for neutron stars, these degeneracy is actually broken. So neutron stars can provide an independent measurement of the redshift. But for current detectors, they are practically not usable for measurement. Of course, people are looking into how we can exploit the physics of neutron stars for redshift measurement for the next generation of detectors. But for current detectors, we cannot really rely on the physics of neutron stars. So what can we rely on? We can rely on the fact that although from a single observation we do not have information, a population of neutron stars can be expected to be at around a certain mass. However, if you observe them from farther away, they would be redshifted to a different mass distribution. So if one knows the mass distribution, the intrinsic mass distribution of neutron stars, if one observes a different mass distribution, then one would know how much this distribution has been redshifted, and one can infer the redshift from a population of distributions. Of course, the redshift would be different for each of the different events, but still one can infer from the different events approximately how much the what the redshift distribution essentially is. Until recently, this idea was there only for neutron star mergers, but it has revived in the context of binary black hole mergers as well, and I'm going to talk a bit about that in some of my later slides. The more direct and perhaps the cleanest measurement of the redshift can come only if you have electromagnetic counterparts. So what would happen if you have an electromagnetic counterpart? One would probably be able to associate the counterpart with the host galaxy, and one can read off the spectral lines in the host galaxy and use the and obtain a redshift. There's the possibility of also obtaining the redshift not from counterparts but from galaxy catalogs. So one has not been able to identify a unique host galaxy, but there's a set of possible galaxies from a galaxy catalog that's going to give us some information as well about the redshift, and we are going to talk about that as well. Furthermore, galaxy clustering or large-scale structuring of matter that sets some kind of a scale, and if one observes the large-scale structure at a certain, if one observes a large-scale structure in a certain redshift shell, it is different from the large-scale structure at a different redshift shell. So if one looks at the large-scale structure in the distance space, that essentially carries information about what the redshift of this, of a certain distance shell is. Again, that is a weak information, but it can be exploited possibly for the next generation. I'm going to talk very briefly about that as well. But let's talk about bright standard sirens first. A clean measurement, distance from the gravitational wave observation, redshift from the electromagnetic counterpart or the host galaxy associated with the electromagnetic counterpart gives us cosmology. We had a binary neutron star merger, GW170817, with an electromagnetic counterpart. We could put these two together and we could obtain a first standard siren measurement in cosmology, which we see here. What is plotted is the posterior probability density. So this is essentially the probability distribution in H0. The peak indicates the most probable value. These are the less probable values. And we compare this with the two measurements in tension. Of course, our errors are much, much wider than any precision cosmology measurement. It's about a 14% error. But the idea is that if one has multiple similar observations, then one can use combined information from many of these and get more and more precise measurements. So typically, the measurement error would scale as 1 over, measurement precision would scale as 1 over square root of the number of detections. If one has a 14% uncertainty at the moment, one would need of the order of 14 squared, which is 200 detections, to go down to a 1% uncertainty. 200 similar detections to go down to a 1% uncertainty. Of course, you might not need a 1% uncertainty to tell which of the two measurements in tension you agree with. There's one important thing to highlight over here, and when I said that the amplitude depends on the distance to the source, I did not tell you that the amplitude also depends on the orientation of the source. So the amplitude depends not only on the distance, but also on the inclination angle of the orientation of a source. In particular, if the source is not face on, but oriented, then the amplitude falls off. So from the amplitude, you do not really know whether the object is farther away or close by and oriented at an angle as opposed to being face on. This results in a degeneracy, in a correlation between the distance and the inclination angle, a degeneracy of the distance with measurement with the inclination, which in turn translates to a degeneracy between the Hubble constant measurement and the inclination. The figure we saw in the previous plot was this particular two-dimensional measurement of Hubble constant marginalized over or integrated over the vertical direction. So we got contribution from this entire from this entire region. However, if one has an independent measurement of the inclination, then one would not need to do the integration over this direction. One can take a slice, one can take a horizontal slice, and one can obtain a much more precise measurement. And with the some of the electromagnetic observations of jets, one could, and the associated jet models, they could already come up with a slightly better measurement of the inclination. If you trust these jet models, then you already get an improved measurement of the Hubble constant. It's important to note that this particular degeneracy between distance and inclination can also be broken by gravitational wave observations alone. If one observes higher harmonics in the signals, that is because the higher harmonics do not fall off in the same way as the lowest order harmonic. And with multiple detectors which make us more sensitive, multiple detectors all over the globe which make us more sensitive to different polarizations, and with signals with higher harmonics, so essentially asymmetric signals, one can hope to break this distance inclination degeneracy better in the future. Let's move over to dark standard sirens. The question now is, what would happen if the electromagnetic counterpart is not observed? As you see, the vast majority, only one signal of these 90 had an electromagnetic counterpart, 1708, 17, yeah, whatever it is. And the rest of them did not have an electromagnetic counterpart. What can we do if no electromagnetic counterpart is observed? Something that one can do is, as I mentioned, one can look for, one can try to identify features in the mass distribution which are robust. So it's argued that the black hole mass distribution is not exactly uniform, but there is a there's an upper cutoff in the intrinsic mass distribution at around 40 or 50 solar masses coming from the pair instability supernova process. And if in the observed distribution, one observes a mass cut in a different range of masses, then that would tell us the redshift distribution of these sources that one is observing. Of course, we do not really know whether there's a sharp mass cut. So a set of papers have shown that even if the mass cut is not sharp, even if there is some feature in the mass distribution, that feature is going to be redshifted and can give us enough information to infer the redshift of the source. An even more agnostic approach is when one does not assume a mass distribution at all. One can try to infer the redshift together with the mass distribution simultaneously. So as we are inferring the mass distribution of the sources which are merging, we also relax the cosmology and we obtain the cosmological parameters simultaneously, giving us already a rough estimate of the cosmological parameters. The second idea comes from galaxy catalogs, and this idea dates back to the first paper by Schutz on standard sirens. The way it works, it's good to go through a set of cartoon animations to demonstrate how it works. So let us first assume that we have a counterpart or an identified galaxy. So one has a distance estimate which comes from the gravitational wave observation, and the unique counterpart or the identified host galaxy gives us a Z value. This gives us a Hubble constant estimate, which is nice and unimodal. We are happy. However, suppose there was no counterpart. So one does not know the exact redshift. However, one knows roughly the region of the sky this event came from. So one can identify a set of galaxies within that sky patch given a certain set of priors. And in this cartoon example, there are 5 possible galaxies. Of course, in reality, there are many, many galaxies and not just 5. So with 5 galaxies in this example, one would obtain 5 peaks in the H0 distribution. Of course, some of the peaks would merge into each other because of the uncertainty coming essentially from the distance, and one would observe essentially a multimodal distribution and not a unimodal distribution. There are 5 peaks here, some of them are merged. So just this measurement is not informative by itself. It does not carry information at all. However, suppose one has a different observation coming from a different part of the sky, a different distance estimate, a different set of galaxies, different set of Z values again taken to be 5, a different multimodal H0 estimate, also not informative by itself. If one stacks up many, many such events, then for all of these H0 estimates, one of the peak is expected to be at the correct location, while all the peaks coming from the incorrect associations are expected to be at random locations. So if one stacks information up from many observed detections, then one would be driven to a joint unimodal result, even though the individual estimates are not informative. This is essentially how this method is supposed to work. In reality, it's a bit more complicated. As we saw already, we are not working with single galaxies, we are working with smear distributions. However, even within a smear distribution, there are overdensities and underdensities. So if we look at a galaxy catalog, we are essentially and use all the Z values from the galaxy catalog, we are essentially tracing the underlying matter distribution. So we are cross-correlating the underlying matter distribution with the distance estimate, the Z values coming from the matter distribution with the DL estimates. And moreover, one can give different weights to different galaxies. So one can give more weights to brighter galaxies, and using this one can improve the efficiency in the method. One can, for example, give a weight in proportion to the luminosity in certain band, in a visible band, if one assumes that these gravitational wave mergers are correlated with the star formation rate, or in an infrared band if one is more agnostic and wants to assume that these gravitational wave mergers are correlated with the total mass of the system. And that leads to an improvement in the measurement. So, an additional complication in this measurement comes from selection effects. So, selection effects will be there on both the gravitational wave side and on the electromagnetic side. Let's first talk about the gravitational wave selection effects. Gravitational wave selection effects would come due to a limited sensitivity of our gravitational wave detectors. So we would not observe all the signals, we would observe only the nearby signals. And if one observes only the nearby signals, even looking at the linear Hubble law dl H0 is ZC, if one has only small values of Z, if one has only small values of distance, one would be biased to high values of H0 just by this linear relationship. In order to undo this, one needs to in order to undo this bias, one needs to calculate the detection efficiency, which is obtained by integrating over all the detectable data sets and putting this detection efficiency in the denominator of the likelihood. However, in order to calculate the detection efficiency, one has to assume the source population parameters. In order to know what kind of sources we will detect, we need to, in order to integrate over all the detectable data sets, we need to know the source population parameters. So this is how the first method that I talked about, inferring H0 from source populations, automatically enters the second method, inferring H0 from galaxy catalogs. The idea is to infer the perfect thing to do would be to infer H0 and a population parameter simultaneously, which is the direction to which we are converging. On the electromagnetic side, there are also selection effects which come from a limited depth of the telescope, leading to incomplete galaxy catalogs. And in order to take care of this, in addition to the in-catalog term, one has to add a contribution expected from the out-of-catalog term. And essentially, with the taking care of the gravitational and the electromagnetic systematic effects, one can expect to obtain an unbiased value of H0. The first realistic dark standard siren measurement essentially came from a paper led by the Dark Energy Survey collaboration together with the LIGO-Virgo collaboration. And we heard about the survey yesterday from Jesse. And they actually coined the term dark standard sirens, which has now become very popular and we are using. So this is the first measurement coming from one very well-localized black hole, GW170814, located in a patch that was very thoroughly followed up by the Dark Energy Survey. Moving more towards the current detections, we have H0 measurement by the LIGO-Virgo collaboration coming only from the source population. So here we do not use any galaxy catalogs. We assume only a mass distribution, that is a power law and a Gaussian peak, and we leave the power law free, the location and the width of the peak free, the relative strength free, and we infer simultaneously the cosmology and the population parameters. We already obtain an improvement with the dark standard sirens over the GW170817 value. Putting in galaxy catalogs, unfortunately, we do not put in the DES catalog here. We only put in catalogs, the Glade catalog, which is more all sky, but not as deep as some of the surveys like DES. We obtain an even further improvement in the H0 measurement. Of course, we are trying to make a precision measurement, so it's important to assure that systematic effects are smaller than statistical uncertainties. At the current stage, so we try to assess all our systematic effects. It turns out that at the current stage, systematic effects coming from population parameters is smaller than systematic effects from galaxy catalog parameters. This is essentially because we do not really have deep galaxy catalogs. So the situation is expected to change with more in-catalog information. And in my group, a student is trying to assess what kind of when systematic effects from galaxy catalogs are going to become important. A summary with results of inclusion from dark standard sirens is over here on the left. You see the result from O2 only, with only a slight improvement over the GW170817 results, and the results from O3, which is a much stronger improvement, again showing us that we are getting we are strongly influenced by the number of detections which we are using. I tried to put these results together in a in a plot like we have seen before, and here we already see the dark siren contribution. Maybe if we have enough detections, we'll be able to resolve the H0 tension with subsequent observations. Once again, we are trying to attempt a precise measurement. We have to be very concerned about accuracy. So we have to be, we have to understand all kinds of systematic effects, which can come from modeling of, which can come from peculiar velocities in the on the electromagnetic side, and other uncertainties from galaxy catalogs, as well as on the gravitational wave side from waveform modeling or detector calibration, although these uncertainties are currently expected to be much lower than the other sources of error. So hopefully with more sources, with rapid follow-up of some of the sources, with early warning that is predicting that a BNS is going to merge even before it has the merger has taken place, we can have more counterpart detections. On the galaxy catalog side, the limitation is incompleteness of galaxy catalogs. Hopefully with upcoming surveys, we are going to have deeper catalogs providing us better redshift information. There are also some prospects of using not galaxy catalogs, but catalogs of galaxy clusters. Of course, we would not have very precise redshift measurement, but given our gravitational wave uncertainties, probably the way galaxy cluster catalogs trace the underlying matter distribution, that is that may be sufficient for cross-correlating with gravitational wave distance observations. I have about 5 minutes, I guess, okay. Or not, okay. Not. Let's see. So the next run of LIGO Virgo is expected to start early next year. A long gap between 03 and 04 is becoming more and more disturbing. We are going to have much smaller sky areas. With 04, the median BNS localization is going to be around 33 square degrees, again, hopefully leading to more efficient follow-up. And there are plans of advanced upgrades to A+ sensitivities when LIGO India is also expected to join. And further down the line, detectors such as the Einstein telescope and Cosmic Explorer are planned, and these detectors are practically going to see all binary black holes or all stellar mass binary black holes which can be observed. For dark standard sirens, there is a bit more to exploit, and this is cross correlations beyond line of sight contribution. So as I said earlier, if one looks at the distance and the redshift distributions and one changes the cosmology, at some cosmology, the fingerprint in the distance distribution is exactly going to match the fingerprint in the redshift distribution, giving us information not from just line of sight correlations, but from beyond the line of sight, effectively making use of gravitational wave sources not as standard sirens, but also as standard rulers. And two groups are following this up are thoroughly following up the prospects of this method. If we're looking years down the line, then current tensions in cosmology may have been resolved, will probably have been resolved, but standard sirens will still remain the direct probe of h of z. So one is still going to measure directly h at whatever redshift or distance we are observing the gravitational wave source, as opposed to using calibrated distance indicator. So one can potentially measure other cosmological parameters such as the dark energy fraction, the matter fraction, or the dark energy equation of state, or even parameters beyond GR such as modified gravity parameters that affect gravitational wave propagation. On the other hand, one can also probe gravitational wave bias. Essentially, we heard about bias or galaxy bias in some of the other talks. This is very similar, but this would be how the gravitational wave source distribution is correlated with the underlying dark matter distribution, and essentially how this factor itself, how this bias itself changes with redshift, changes with direction, changes with masses which we are observing. One can also, because these third generation of detectors give us sky areas of less than a square degree, one can think of probing the universe with gravitational wave observations alone, not using cross correlations. And some authors have shown that we are already able to resolve the BAO peak with 3G gravitational wave observations. However, with 3G, we are going to have a different set of challenges. We are going to have so many signals that we are going to run into data analysis challenges. We are going to have very long signals and overlapping, which would overlap with each other, and this really needs some rethinking in the way we do our current data analysis. This is my last slide, sorry for going a bit over time. And this shows the various bands in which we observe gravitational waves. Here's a frequency. This is the current LIGO-Virgo sensitivity, the sensitivity of the Einstein telescope or Cosmic Explorer, which is very similar. However, we are going to observe, we are hopefully going to have also space-based interferometers such as LISA, which are going to observe in a millihertz band, and there are also other methods, completely different methods of observing gravitational waves, not by interferometers, but by looking at pulsars and seeing how these pulsars are slowed down or sped up as the gravitational waves are passing through them, the international with pulsar timing arrays, and with this wide range of detectors, the prospects of science in general and cosmology in particular with gravitational waves is very exciting. I'd like to thank you for your attention.
Hi, thanks for the talk. So how, as you get more accuracy and the signals, you can watch them for a longer period of time, do they ever get long enough that it actually helps you pinpointing where it's coming from and improving the accuracy of the angular determination? Because once you start to look at it in different angles from the same interferometer, then I guess I would imagine that you start pinpointing better that source. So it's not so much what is the instantaneous pinpointing that matters, but this for a long signal, that's a different calculation, or is it never long enough that this really counts?
So for LISA, that is absolutely true. So for LISA, you're observing signals for so long that you have essentially seen it from various different angles. But for 3G detectors, we are not there yet. I mean, they are long, but not, we of course do better because we observe it from different orientations, so that definitely improves, but not to the extent of LISA. I hope this answers your question.
But if they last so long that the Earth's movement,
so essentially the Earth is moving, so the detectors themselves are moving. So as the detectors are moving, you are observing the system from different angles, you are probing different polarizations, and this improves essentially the whole of parameter estimation of the signals.
So you talk about
Let me just point out, I mean, the thing is, for ET, the signals are long in the sense it goes on to minutes, from minutes to hours, but not usually not days or years, which is. Yeah.
So you were talking about when you have several redshift possibilities for one luminosity distance estimate, and so you get an H0 with several peaks. How I didn't understand how you combine these H0 estimates to give a.
Okay, so by the way, this is only a cartoon. It's in practice, as you saw from the real results, even with one observation, you do not see a clear multiple peaks. You just see a vague underlying redshift imprint of the underlying redshift distribution. The idea is that for all these peaks, okay, for this observation, one of the peaks is coming from a correct association, the other peaks are coming from random associations. If it is coming from the correct association, then it is going to be at the correct value of H0, whatever it is, right? So this peak at the correct location will be located at 70 kilometers per second per megaparsec. This peak at the correct location will be 70 kilometers per second per megaparsec. So at 70 kilometers per second per megaparsec, you would always see a peak, while the other peaks would be at random locations. They would be there in some of these, they would not be there in some of the others.
So you take a difference between the.
No, you combine by multiplying all these together. Okay, that's how you combine likelihood. So you use the posterior of the previous experiment, posterior coming from the previous experiment as the prior for the next experiment. So you essentially end up multiplying all the likelihoods. So you multiply all these distributions, then the peak at the right location would get enhanced, while the peaks at the other locations would get suppressed. So this is a very simplistic cartoon, but we have also done some simulations which go beyond the simplistic cartoon, and we have also demonstrated that this works even when we have not 5 but 500 galaxies in the patch.
Okay, so can you go to slide 33?
Yeah.
No, sorry. I think it is the one that you have the error bars for the H0 from Cepheids and
this one?
no, it's way. Okay, but I think I can do the.
Or was it 34?
Yeah, maybe.
This one?
Yes, yes.
Okay.
So if I'm not mistaken, you said that the blue error bar falls with 1 over the square root of the number of detections, right?
Yeah.
So given the current rhythm of detections with electromagnetic counterparts, how much time do you think it will be necessary for you to...
Okay, Ricardo just left. And yesterday I had a bet with Ricardo that by 2032...
I was present.
You were present. by 2032, we will see bright standard. We will see bright standard sirens, and Ricardo said that we will not see bright standard sirens. I know that Luis here says we will not see 50 bright standard sirens. I don't know. It's definitely very unclear at this stage. It depends on a number of things. It depends on the rate at which you observe the binary neutron stars.
But sure assuming the current rate.
Okay, we have observed one neutron star, essentially two more or less clear binary neutron stars, right? So it's a very low number statistics at the moment. So it depends not only on the rate of neutron star mergers, it also depends on how rapidly we can follow them up. Given the sky areas, okay, the sky patches are going to improve. Then there are other considerations also. How many of these would have bright counterparts? I mean, if you observe neutron star mergers even at 300 megaparsecs, you would not be able to see an optical counterpart. The counterpart itself may be intrinsically dim. For example, for the heavy neutron star, which I talked about, there's a possibility that there was a counterpart, but it was so dim that it couldn't have been followed up. For heavy systems which collapse promptly into a black hole, the counterpart is expected to be dim. So because of these considerations, it becomes very difficult to promise a certain number of bright detections.
So can I have, okay, it's the last one. You talk about sources that have electromagnetic signals as a counterpart. Could you talk about sources in which you have electromagnetic signals as a counterpart?
Yeah.
For the estimation of H naught?
Yeah.
Can you have sources with other kinds of signals that can be used as counterparts?
Like neutrinos?
Yes, for example.
It would be okay. It would be reasonably difficult because the neutrino energies are quite difficult to predict. It would not come with a sharp energy, right? So the only thing that you can see for neutrinos is the energy, and I do not see very strong prospects of using neutrinos as distance or redshift indicators.
Okay, thank you.
Hi, thank you for the presentation. I would like to ask what would be the implications of the gravitational standard sirens measurements of the Hubble constant converging for each of the two current measurements, the Cepheids or the CMB, or even a third value of the...
So you were saying, your question is what would happen if we end up agreeing with the Planck measurement, and what would be the implication if we agree with the Planck measurement, and what would be implication if we have to agree with the...
or even a different value of these two.
That would be even more exciting. Okay, so the thing is, if we agree with the Planck measurement, then that would probably signal that there is some... I mentioned it in my other plot, yeah. So if we agree with the Planck measurement, then that would signal that there is probably some problem with the calibration of the supernova results. I mean, this is also particularly, many of you would know better than me about this. This would could be because there are many steps in calibration which go in here. So if everything else agrees with this and supernova measurements stand out, there's some problem with the calibration on this side. While if we agree with the supernova measurement, so that means that all the local measurements agree, while all the measurements or the measurements from the early universe, they disagree with the local measurements. And a cosmological model has gone into obtaining Hubble parameter in the current epoch from the early universe. So if we agree with the supernova measurements, that would signal that a problem with the cosmological model, the lambda CDM model.
Questions? I do have a question. So with the third generation detectors, we're gonna see a lot of events. So at which point, so how often, because if there are many events at the same time and they're faint, they become background at some point, gravitational wave background, right? Or yeah. We'd always be able to distinguish and detect single events?
No, so the idea is these events would be in the foreground, so one would see a coherent signal from these events.
But could it be like you have tens of events at the same time and they cannot distinguish between them, or you'll always be able to?
Sorry, where was I? No. It's one is not looking at many. One is not looking at order of 100 events at the same time. So of the fact 2 or 3 events at the same time, and one would be able to distinguish between them because one important thing is even if they're in the same, all in the band in the same time, they're merging at different times, right? So there you see a very clear signal from the merger. So the searches would very clearly tell you this is where one event is. Then you can essentially use that information and you can in some sense try to take that bit out, use the merger and then take that bit out. You're left with the residual with the rest of the signal and do a parameter inference for the other signal when it's merging. So this is essentially what helps us.
Okay. Other questions?
It's on a comment. In that plot that you showed the signal-to-noise ratio, passing the template around the output of your detector, if you have a lot of signals over there, you could see a lot of peaks in the signal-to-noise ratio.
Yeah.
And this could be used to distinguish many different signals that you have in the output of your detector. Suppose you have 2 gravitational waves passing your output of your detector, and you will see 2 peaks of the signal-to-noise ratio. Yes?
Yeah.
Could be used,
Yeah. So that's what I meant. So the thing is, the search itself would show all the interesting would show all the mergers. Yeah.
Okay, so
Questions?
we close here. So thank you again.